Howdy, folks. Let's look at Chapter 4, Section 2 today, and this is about, again, higher order differential equations, but what we are going to do is, suppose you have a second order differential equation and you know one solution. How do you construct a second solution from that known solution? That's what this is all about, okay? So let me give you a few more details about it. One of the first things that I need to tell you is, what in the world is a higher order linear homogeneous equation? Now there's this word again, homogeneous, but in this context, in the context of higher order equations, it has a completely different meaning. If you remember, when we were talking about first order equations, homogeneous meant a certain thing. You would say an equation is homogeneous if m of xy and n of xy are homogeneous functions. And what did that in turn mean? M of tx comma ty is equal to t to the n times m of xy, and similarly n of tx comma ty is t to the n times n of xy, right? So it was slightly more complicated. Fortunately, for higher order equations, homogeneous means very simple. The right hand side is 0. That's it. So check this out. Does this ring a bell, the left hand side? Yeah, that's the nth order linear equation. You have the nth derivative d to the ny dx to the n. Its coefficient is just a function of x, and so on. Right? You're familiar with this one. But the only thing is, earlier this was g of x, but now g of x is specifically 0. That's the idea. That's a homogeneous equation. And our intention is to solve a linear homogeneous ordinary differential equation of this kind. Now, one of the things that happens with such equations is you will have n linearly independent solutions. And what? Linearly independent solutions. Now you see why we needed to learn about linearly independent functions back in the previous section. Because it applies here. The solutions that you find for a higher order linear homogeneous equation must be linearly independent. If not, you have really not found all the n solutions of an nth order differential equation. Okay? All right. So let me, as a motivation, show you what in the world I mean by this. Is y equal to sin x a solution of y double prime plus y equal to 0? How do you proceed? Oh, simple. Figure out y prime and y double prime, plug and see whether left hand side equals right hand side. And sure enough, y prime is cosine x, y double prime is negative sin x. Left hand side is equal to right hand side. Okay? Now, let's see. Is this y double prime plus y equal to 0? Is that a linear second order equation? Yep, coefficient of y double prime is 1. Y double prime is raised to a power of 1. That's good. And there is no y prime term. That means its coefficient was 0. And y's coefficient is 1. That's also a function of x. Y is being raised to a power of 1. That's good. Is it homogeneous? Yep, simply because the right hand side happens to be 0. Okay. So, according to the statement that I showed you previously in the previous slide, this one, such an equation has n linearly independent solutions. How many solutions should our problem have? Because it's a second order homogeneous linear, must have 2 solutions. Have I already demonstrated that y equals sin x is one such solution? Yep, it is. So is there another solution to this? There must be. And that must be linearly independent too. So that's what motivates me to asking you this question. Is y equals cosine x a solution? Turns out, yes, even if you were to do the same thing as you did for sine x with cosine x, you will notice that left hand side equals right hand side, and cosine x certainly satisfies this equation. So at least here we see an example where we have a second order homogeneous equation and it does have two linearly independent solutions, sine x and cosine x. Can I really claim that sine x and cosine x are linearly independent? Yes, I can. Because if you say compute the Wronskian is sine x and cosine x, and its derivatives are cosine x and negative sine x, and the Wronskian itself is negative sine square x. I mean, the determinant is negative sine square x minus cosine square x. This is negative 1, and this is not equal to 0 for all x. In this, these both functions are defined, I can go ahead and say R. Both functions are defined everywhere from negative infinity to infinity. So on the entire interval of real numbers, sine x and cosine x are certainly linearly independent. And just as that statement said, for a second order homogeneous linear equation, we did find two linearly independent solutions. That's the main point I'm trying to convey. Okay? With that, what we will look at is, if we were to have a second order linearly independent, we have a second order homogeneous equation, linear, like this, a2 of x second d square y dx square, or y double prime, and so on. And if you know one solution, say y sub 1, how do you find the second solution, y sub 2? Not just the second solution, it better be the linearly independent second solution. How do you find that? There is a process to it. Why the process works, I will explain toward the end of the slides. But right now, you just try to familiarize yourself with the process. This is how you find. So let me describe the problem once again so it is crystal clear in your heads. If you have a second order linear homogeneous equation and you know one solution y sub 1, how do you find the second solution y2? And here, first divide throughout by a2 of x, and right hand side 0 over a2 of x is 0. The idea there being a2 of x will never be 0. If it were, then you would bump into 0 over 0, which is not a good idea, right? So a2 of x will never be 0, so everything is fine and dandy with this. And what is p of x? Clearly a1 of x over a2 of x. What is q of x? a0 of x over a2 of x, right? So given an equation like this, you do this, you write in this form, and basically you are picking this p of x especially. You really don't care about the q of x. Well, not for the second solution. It turns out the first solution depends on q of x, but not the second solution. Okay, so y2, the second solution, is y1, the first solution, times a certain integral. Okay, you need to memorize this thing. Integral e raised to negative integral of p of x dx over y1 square dx. Now, if you look at this just a tad carefully, it almost looks like our mu, right? In first order linear equations we did e raised to integral of p of x dx is our mu. This is almost like that, except that you have to do e raised to negative integral of p of x dx. Okay, and p of x is the coefficient of dy dx. So there are some differences, but there are also some similarities. That's the point I'm trying to make. Divided by y1 square. We already know y1, the first solution. So now if you evaluate this integral with respect to x, and multiply by y1, you get the second solution. Cool. As simple and straightforward as that. So let's solve a few problems to solidify the concept. Suppose you have y double prime plus 2y prime plus y equal to 0. Is that, what order is it? Second. Is that linear? Yep, all the coefficients are constants. Yep, so it is linear. Is this homogeneous? Yep, simply because the right hand side is 0. Okay. And one of the solutions, the first solution, is x e to the negative x apparently. And we are asked to find the second linearly independent solution, y2. Now, recall, how do you find y2? This is the formula. Cool? Now, I had sort of challenged you in section 2.5, first order linear equations. Hey, I came up with these steps to solve, steps 1 through 6 or something like that, and said, could you have come up with those steps yourself? And I said, yeah, you would. If you thought in a logical fashion, you would have come up with those steps yourself. The reason I'm talking about that is, I want to make that challenge once again to you. Look at this whole thing. What is it that we need to do? We need to find the left-hand side stuff. This is the unknown. y2 is the unknown. Is y1 a known quantity? Yep, that y1 is x e to the negative x in this case. So that usually will be a known quantity. And we need to integrate e raised to negative integral of p of x dx. So, do we need to know what p of x is to begin with? Yeah, if we know what p of x is, that would be our first step, so that we can integrate integral of p of x dx, or in fact negative integral of p of x dx we will find. After that, we'll find e raised to negative integral of p of x dx in the next step. You see, wouldn't that be the order? Find p of x, find integral of p of x, find e raised to negative integral of p of x. These are all the steps. And once you got the numerator, now divide that numerator by y1 square and integrate the whole thing with respect to x. And finally multiply by y1, you're done. Right? So that is exactly what I'm going to do. As I told you, p of x. I figured out what p of x is. Well, we didn't even need to divide by the coefficient of y double prime because it's already 1. And so we just read off what the coefficient of y prime is, which happens to be 2. So p of x is 2. And I'm figuring out negative integral of p of x 2x. I could have done integral of p of x and then stuck in negative later. But negative integral of p of x is negative 2x. And what is e raised to negative integral of p of x dx? Oh, in this case, e raised to negative 2x. Cool. And the next step should be that e raised to negative integral of p of x dx divided by y1 square and integrate. That's exactly what I did. I figured out that integral. Alright, so let's look at the integral a little. E to the negative 2x, fine. y1 happens to be x e to the negative x. So I have x e to the negative x, the quantity square. Right? What would this be? Wouldn't this become x square times e to the negative 2x? Right? X square times e to the negative 2x? Yeah. So, there's an e to the negative 2x and the e to the negative 2x there. That reduces to 1 over x square. What's integral of 1 over x square? Negative 1 over x. Right? So what have we found so far? We found this entire integral. What is left to find y2? We just need to multiply that integral with a y1. That's exactly what we'll do. y2 is y1 times that integral. y1 happens to be x e to the negative x. The integral happens to be negative 1 over x. Multiply, you get negative e to the negative x. That's the second solution that we are looking for. But I'm about to say something here interesting. For a linear homogeneous equation, if y is a solution, then a constant multiple is also a solution. What does that mean? What that means is, did we say x e to the negative x is a solution of this linear homogeneous equation? Yep. Suppose I were to multiply this by 2 and make it 2x e to the negative x. Would that be a solution? Guaranteed. In fact, I could multiply this solution by any constant and that would still be a solution of this differential equation. That's the nature of linear equations. See, one of the, I told you way in the beginning, why do you care about this stupid linear, man? It's because it has all these wonderful properties. If y1 is a solution, then any constant multiple of it is also a solution, is the idea. Okay? So, why am I saying that here? And I'm saying that because, so without loss of generality, that's what this WLOG means. Without loss of generality, meaning it's okay if you do this kind of a thing. You won't be altering anything in a significant way. We got y2 to be negative e to the negative x, right? Can I multiply this by some constant and would that be a solution? Yes. So like, could I multiply this by 2? Yes. By pi? Yes. By negative 1? Yes. I like that negative 1. Why? Because if I multiply by negative 1, this just becomes e to the negative x. Yeah, I like that. Negative e to the negative x and e to the negative x. Which one is better sounding? I think e to the negative x. So that's why we just say e to the negative x. Simple? So there we go. For this differential equation, apparently x e to the negative x is one solution, and the second solution, second linearly independent solution, is e to the negative x. So we found two linearly independent solutions, and that's the whole idea. Cool. Similar problem, given this differential equation and y1 equals x squared, find y2. I'll put that formula again. When I do problems like this, I keep on writing that formula over and over again. For every problem, I'll just write it. The more number of times I write it, the better I can commit it to memory. Okay? All right. First order of business, find p of x. To do that, what? Divide throughout by x squared. And that's exactly what I did. P of x is the coefficient of y prime. So P of x is 2 over x. Then figure out negative integral of P of x dx. And so that turns out to be negative 2 natural log of x, or we can write that as natural log of x to the negative 2. Right? And let's figure out e raised to negative integral of P of x dx next, which turns out to be x to the negative 2. And then step after that, let's divide this guy by y1 square, and that gives us x to the negative 6. So that means the integral is negative x to the 5 over 5. And what's left? We figured out the integral, just we need to multiply by y1, and that's exactly what I'm about to do. So when I do, negative 1/5 x to the negative 3. Okay, this is what we seem to be getting as a second solution. could we, without loss of generality, multiply this by some suitable constant so that we don't have this annoying negative 1/5? Yeah, if you multiply by -5, this just becomes x to the -3. And so that's exactly what I did. Now you might, well, will you take off any points if we just left it as -1/5? Maybe 1 point. Because I do want you to recognize that, hey, you don't need to carry stupid constant multiples like that, and you can just make that into just 1. Okay? So maybe 1 point. So here we go. This is the second solution. I think this is fairly straightforward, right? Just a simple step-by-step process and you're done. So let's look at a slightly more complicated problem. Second order, linear, homogeneous. One solution is known. What is the second solution? So first step, divide throughout by the coefficient of y double prime, and we end up with this. Figure p of x from this, which turns out to be the coefficient of y prime, this guy. Negative integral of p of x dx is what we need to find. Okay. Now notice what I did here. To integrate negative integral of p of x dx, you plug that p of x into the integral. But what happened to the negative sign? Well, I used that negative sign to multiply the denominator. Or maybe, I don't know, see if this would make sense. I'm supposed to have a negative sign, right? Now, can I multiply both the top and the bottom by -1? Right? So when I do that, negative times -1, that becomes positive for the top. So I left it as a positive 2 times 1 plus x on the top. But the bottom should be multiplied by -1. Bottom of this p of x should be multiplied by -1. So that makes this -1 plus 2x plus x squared, which I wrote as x squared plus 2x minus 1. There's a reason why I did this. If we do a u substitution, u equals the denominator, would we get du to be 2x plus 2, the quantity times dx? Isn't that 2 times x plus 1 dx, which is what the top is? So this whole integral becomes du over u, which is natural log of u. Absolute value of u, but we'll assume that we can find a suitable range for x, say a suitable interval for x. Okay, so this is just simply natural log of x squared plus 2x minus 1. And e raised to this should be x squared plus 2x minus 1. What's the next step then? We figured out the top, e raised to negative integral period. We need to divide that by y1 square and integrate. That's exactly what I'm doing. Whoa. How do we integrate this guy? I notice that this is x squared plus 2x minus 1, whereas we have an x plus 1, the quantity square. X plus 1, the quantity square, when you FOIL that out, you get x squared plus 2x plus 1. Sort of very similar to this guy, right? So what I'll do is, first I will write this x plus 1, the quantity square. Okay, I just wanted to show you this, I guess. But then, can I say the top is exactly what the denominator is, x squared plus 2x plus 1? But then I'll subtract 2 from it. Like that. Now I can separate this into 2 fractions. All of this stuff over this minus 2 over this. So this is a partial fraction decomposition. by a clever method. Okay, what you could have done to get the same thing is you could have done a long division of the numerator with the denominator, and you would have gotten the same thing. But where this seems like a easy enough manipulation for me to figure out, so that's what I did. So integral of 1 is simply x, and integral of negative 2 over x plus 1 square turns out to be 2 over x plus 1. So plus 2 over x plus 1. So x plus 2 over x plus 1. And so we have x plus 1 times 2, that reduces to this. And the whole thing is x squared plus x plus 2. Isn't that interesting? That's a very interesting problem. And one thing I have not done so far is I didn't check whether y1 and y2 are linearly independent. It's not enough if you find a second solution. You must find a second linearly independent solution. What do you mean? Why do you put that restriction if you ask? Could you do this if that is the case? I give you y1 equals x plus 1, and I ask you, well, that's one solution. Tell me what is the second solution? And you'll say, I'm going to multiply this by 2, and that's going to be definitely a solution. So you will say, you asked me for a second solution, I found it. Well, you didn't quite find a linearly independent solution. Yes, you did find a second solution, but it is not a linearly independent solution of the first. And that's the insistence. Okay. Now, the thing is, when you go through this process, the solution that comes out is automatically linearly independent. That's the beauty of this process. That's why I didn't even bother to check whether y1 and y2 are linearly independent. They are guaranteed to be linearly independent. Cool? Next, we have a problem like this, and same steps. Negative 3 over x is a p of x. Negative integral of p of x turns out to be natural log of x cubed. And e raised to that would be just x cubed. X cubed divided by x squared cosine of blah blah. Whoa. Can I? X cubed, and in the denominator would we have x to the 4? Yep, x cubed over x to the 4 is 1 over x. In the denominator, do we have a cosine square of natural log of x? Yep, 1 over cosine square of natural log of x is secant square of natural log of x, right? Secant square of natural log of x over x. So the question is, how do you integrate this? Use substitution. If you say u equals natural log of x, du is 1 over x dx. So this is just integral secant square u du. Tangent u is the integral. So tangent of natural log of x is the integral. Okay, what's the next step? Multiplying by y1. y1 turned out to be x squared cosine of natural log of x. We just found this integral to be tangent of natural log of x. And that becomes x squared sine of natural log of x. What? How? Well, can I write tangent of natural log of x as sine of natural log of x over cosine of natural log of x? Do cosine of natural log of x cancel each other? So wouldn't we left with sine of natural log of x? There you go. So that's the second solution. Cool. This is how you solve this one. Why does this process work? Okay, this is for people who are interested. Take a look at this one. Suppose you were to assume that y2 is equal to y1 times u. Okay, there is some function called u that you will need to multiply this y1 by, and that's how you get y2. Let us say we assume that. Now, you could very well ask, how can you assume that? Well, some genius guy some time back did that. Genius guy or girl. And when they did that, they were able to find such a u. And then from then on, we are all shamelessly copying that process. As simple as that. Okay, y2 equals, assume that is y1 times some u. Well, if y2 is a solution, then we should be able to plug that into the differential equation, and the left-hand side must equal right-hand side. And in order to be able to do that, I figured out what y2 prime and y2 double prime are. And there's some mathematics here, simple algebra there. And then when I plug here, which is nothing but that differential equation where I have a y double prime, I plugged in y2 double prime, this stuff, y1 u double prime plus all of this. And in the next step, I separated the terms with just a u in it. And turns out there is a y1 double prime, and there is a p of x y1 prime, and there is a q of x y1. Similarly, I picked up all the terms with a u prime in it and get this one, and a u double prime. But this quantity happens to be 0, must be 0. Why? That is because y1 is a solution, which means if you plug in y1 double prime plus, that must be 0. So the whole thing disappears. And this, it leaves us with this simpler equation. What good did it do? Well, we seem to have a second order differential equation now. But in reality, this is not quite a second order differential equation. That is because the moment we plug in w equals u prime, which means w prime is u double prime, this equation reduces to y1 w prime, the first term, this becomes y1 w prime, plus all of this times just w, because u prime is w, and that's equal to 0. Right? So this is a first order equation in w. And the thing is, we know exactly how to solve first order equations. How? Check this out. I divided throughout by y1 and ended up with this. And then dw dx is equal to negative of this, right? And then use separation of variables, dw over w equals all of this stuff times dx, and integrated both sides. Integral dw over w is natural log of w. Let's assume that w is positive. And now, how do we integrate this part? That's the part that I may need to show you a little. Can I split this into two integrals? Right? We have a sum of integrals. So integral of a sum equals sum of integrals. So I split this into two. Negative 2 y1 prime over y1 dx, and the negative p integral p of x dx. What is integral of y1 prime over y1 dx? If we did a substitution, for example, I don't want to say u, v, let us say, v is y1, dv is y1 prime dx, right? So basically this whole thing reduces to dv over v, which is natural log of v, and v happens to be y1. So this simply becomes, this integral becomes negative 2 natural log of v, or v is y1, so negative 2 natural log of y1. And this other integral, let's just leave it like that. Or we can write this as natural log of 1 over y1 square. What are we trying to do? We are trying to find what that u is that you need to multiply this y1 with. So here we got to natural log of w being equal to this stuff. And so w itself would be e raised to this. And this is in the form of a raised to m plus n, which is a raised to m times a raised to n. So e to the natural log of 1 over y1 square, which is nothing but 1 over y1 square, times e raised to negative integral of p of x dx. So w is this guy. And how do you get u from w? Well, w is u prime. So u itself is integral of w. That's exactly what I did. I said u equals integral of w, which is what this quantity is. Cool? That's it. So this is where that multiplying factor comes from. Once again, if you understood it, wonderful. If you didn't, equally wonderful. Don't worry about it.